So another important concept is this notion of periodicity or aperiodicity. So we like irreducible chains. We also will like aperiodic ones. Essentially, we want statements like this to hold, and essentially, it's not exactly true, but it's essentially the only way that this fails to hold is when you have a periodic Markov chain. So let's look at the notion of periodicity. A period of a state x, which I'm going to denote by px, of a Markov chain, right? So we have states of a Markov chain, and we're going to give them numbers px. Each one of them is going to denote the period of that state. It is the greatest common divisor. Let's unpack that in a little bit, of this set of numbers. So first, let me go through what these numbers are. These are sets of times. That's what they are. They are, moreover, return times of positive probability, right? So this is the probability that x naught, x0 starts at x, and at time k, it's equal to x again, right? So this is a return probability in k steps. And this is collecting all of these return times which satisfy this condition, meaning you return with positive probability in k steps. Now, when it's possible for the set to be empty, right, meaning that there's no way to return to a state. We just saw an example of this on the previous clip, where you kind of leave a state and you just never return to it. And in that case, the period is defined to be 0, for lack of a better number. Here I wrote down just a different way to think about, but the same way of defining the state ix of return times of positive probability is just to write them in terms of the k-step transition probability, right? This is nothing other than starting from state x and returning to, again, to state x in k steps. One difference you can kind of note is that, this technically applies to time inhomogeneous chains, the way I've written here, whereas this k-step transition probability, already, kind of inherently carries with the notion of time homogeneity. It doesn't matter when you started, right? Here, this basically says you're starting at time 0, but it's a small kind of point having to do with notation. So a chain is aperiodic if every single period is less than or equal to 1, which basically says that the period of every state is either 1 or you never come back to it. And before we discuss sort of, there's a trick to make a chain aperiodic. And before that, let's look at some examples of periodic chains. So the most kind of canonical example is this one. Let's first try to write down what ix it would be for any one of these states, right? Clearly there's some symmetry here, so whatever the state is for state 1, it would be the same for state 2. And the question is, how do I return, right? Well, I return always in the exact same way. I move over to 2 and then I come back, right? So I can come back in steps 2 by just going 1, 2, but I can also return again in step 4 by moving to 2 and then back, right? So 4, and then same thing with 6. So I can go 5, 6, 7, 8, right, 9, 10, and so on. So in the set ix for, let's say, x equals 1, you will see the numbers 2, 4, 6, 8, 10, and so on. Multiples of 2. In fact, multiples of the period. So greatest common divisor is the largest number dividing every single one of the numbers in ix without a remainder. And what you can ask, what's the greatest number dividing the set 2, the set of essentially all even numbers, right? 2, 4, 6, 8, those are all even numbers. What's the largest one that divides all of them without a remainder? Well, that's 2, right? So another way to think about of the period is ways of coming back, returning to a state in multiples of the period, right? So whenever a state has period px, you can return with positive probability in multiples of px. And so in here, px, or p1 in this case, is equal to 2, and same thing for 2. You can come back to this state in multiples of 2. This is an example where you return in multiples of 3, right? If I start with state 3 and I move 1, 2, 3, right, 4, 5, 6, and so on 6, right, then 9, then 12, and so on and so forth. In both of these examples, you can very quickly verify this condition. The stationary distribution exists in both of them, and in fact it's completely ambiguous or kind of arbitrary in sort of assigning the values, right? It's for the stationary distribution, there's no way to distinguish the sets, states 1 and 2, right? So here the stationary distribution is just 1/2 on each state. However, these one-step transition probabilities will oscillate depending on whether you're taking an even or odd number of states. Same thing happens here. The stationary distribution is 1/3, 1/3, 1/3, and you have the same sort of flipping deterministic behavior of pxk depending on whether k is a multiple of 3, the period, which is 3, you have a 0 or a 1. Finally, let's look through an example and try to show that this is not, or rather this is aperiodic or not periodic. So you can start with state 6, and let's list all return times that have positive probability. So 2 is one of them, right? 1, 2. And notice this didn't have to happen with probability 1 like it did over here. So potentially or clearly you have 2 transitions of positive probability, and so I just chose to take this one. And so this one has a return time of positive probability of time of 2. Then you can go 1, 2, 3, and so now I've already written down the numbers 2 and 3 in the state I6, right? I6 is this list of numbers for state 6 for this chain here. And once I've written down 2 and 3, these are relatively prime, right? And so you're not gonna, the largest number that can divide both of those is 1, and I don't need to keep making a list, right? Because no matter what numbers you add on top of that, I'm not going to be able to get a greater common divisor, right? 2 and 3 already seal the deal. So the period of this state, at least, is 1, right? And you can try to go through and make sure that this is the case with all states, but kind of it's already suggestive that if you start at any other state and you're going to have to hit 6 at some point, and that's already aperiodic, and so this is a pretty simple exercise to show that this is an aperiodic Markov chain. There is a few more things I want to say. You can think of, one could ask, what is the, you can consider this entire set of states as one Markov chain, right? And you can see how there's no unified definition for the period of this Markov chain. There are some subsets of states that have period 2. Here you have a section that has period 3. Here you have a section that's aperiodic, right? So there's no way to define a period to all of the states or to the entire chain, but it is possible to do it on a per state basis. And so you have this similar concept with irreducibility. Sometimes you want to throw out a bunch of states to keep the good part, right? So here I would throw out everything to the left of this line, right, and then keep the good part, the aperiodic part, because there you can get a limit like this to actually hold. One more, let's see if there's one more thing that I want to say, which relates to, actually maybe 2 things I want to say. So yeah, one thing that I'd like to say is that these 2 examples are a little bit kind of superficial in the sense that you're always returning in a multiple of 2, right, in here. And that's going to be true, but the point is that in here you can't return in you return in 2 at first, but you cannot return in 4 steps without returning in 2 steps beforehand, right? If I say I'm going to return here in 4 steps, I would have returned in 2 before I would have counted 4, and so that seems you could ask, is that always the case? And it's not. Let me show you. So I want to specifically point out the very last example on the bottom of this drawing, which the period here, if you write it out, you'll see the period is 3 in IX you will see numbers, 3, 6, 9, and so on, multiples of 3, multiples of the period. And here you don't have the same sort of property that you return always in 3 before you return in 6. So for example, I can move from A to C, right, in 2 steps and then return on the third. However, I can keep going, right, and return, once I hit E, I'm already at 2, 3, 4 steps that I can go 5 and then 6. So the very first time I return here would have been in 6 steps, right? So this is clearly what I've drawn here is not, the only kind of possible. You get more complex cases for how you return back to the original state. So don't think of it as I'm always going to, if the period is 3, which it is in this very bottom example, the period here is 3, that doesn't mean you're always going to return in 3 steps. It means you're going to return in a multiple of 3, right? And clearly you can see a path that returns in precisely 3 steps, and then you can see that one that returns precisely in 6 steps. And then if you go all the way from A to G, and then skipping back to E, C, A, you'll return in 9 steps. You can also, if you want to kind of think through some other examples, A and B both have period 2, as I see it. So I think the answer, you can check me on this in screenshot, in figure A, has got to be period 2, even though here again, you're not always going to return after 2 steps, but you're going to return in a multiple of 2. And so the period of that, of all states there is 2. And then on the right-hand side, figure B, I believe the period there also looks like, to me, like it's 2, 3. Yeah, but again, you don't necessarily return just after a period number of states. You don't necessarily return after 2 steps. You can return after 4, and maybe even longer, right? So I guess after 4 steps, you maybe have to return. No, you don't have to return. Yeah. So anyway, these are kind of slightly more complicated things, complicated chains to think through to make sure you understand the concept. And then finally, you can, here's, somebody gives you, you're at your job and you have this Markov chain, and unfortunately you find out that it's periodic, and for whatever reason, maybe this one you don't like that. You can always fix things by adding a self transition. So if I were to take this chain, subtract an epsilon from this transition probability, epsilon is always a tiny number, like even if it's 0 with a 0.0 billion zeros and a 1, and then I'm going to add a self transition with probability epsilon. That tiny transition will fix this aperiodicity condition. The reason behind this is that look what's happening with state 4 here. It can always return in 1 step, and so you have, as soon as the number 1 appears in IX, you're done, right? Because at that point you're qualified for a state of period 1. So, and you can think about how that extends to a larger argument where you have some very complicated chain, regardless of how complicated, and it has a period that's greater than 1. Adding a self transition will immediately ensure that all states have a period less than or equal to 1, right? And so hopefully you can kind of think through that exercise on your own. Not only am I fixing the period of this state by adding this transition, I'm fixing the period of all states, right? And the hint there is that starting from any other state, you can get to this one and then add any number of kind of cycles to break this greatest common divisor criterion. So that's a good thing to think through, but I think it's enough for this concept for the time being.